Hello everyone, we are now going to start the physicist debate, and what I'm going to do is I'm going to introduce Chris. This is a gentleman that I've been liaising with over the last 4 months maybe, and this is exciting at the same time scary because we do not know how this is going to go. And I do not mean reference their answers, but the process on how to actually ask a question, get an answer. And even though there's people on the internet watching this now thinking it's easy, please come up. So anyway, I'm going to introduce you to Chris, and then the three guys here, and I think we all got your name. Oh, we got Tom. I know you're going to introduce him, but we've got Luke, may the force be with you, and we have George Lucas. So anyway, Chris is going to introduce.
All right. Down a little bit. Tall guy. So yeah, thanks very much, Gary. Just to provide a little bit of context before we kick things off. Met some of you in the breaks, but my name's Chris Richardson. I'm a journalist based at Imperial College down in London. I'm the editor-in-chief at a quarterly science publication there, and initially got in touch with Gary about an article I was putting together about truth and how observations become theories, become facts, and that entire process, and the scientific method, and so on and so forth. And after a few initial conversations, it became apparent that rather than just coming here to put that article together, it might be quite useful if I tapped into the network of scientists at Imperial College to find some physicists from mainstream science who might be willing to come and speak today and provide an alternative viewpoint to the types of things that you've been hearing about throughout this weekend. So, as a journalist, I'm interested in challenging conventional wisdom. As someone with a scientific background, I believe strongly in the power of empirical data and also testing hypotheses and the rigorous scientific method that we have, although it does have some limitations. That said, as a person, I think there are many things hidden in plain sight that aren't quite as they seem. So a government, I think that's a topic that's come up quite a lot this weekend. A government I see as a large gang with a monopoly of force. Borders are arbitrary lines that are drawn in the sand, and money only has as much power as we're willing to give it. All of that in mind, I'm still not of the opinion that the Earth is flat. However, I think one of the greatest values we can have as individuals is the ability to change our minds in the face of new evidence. So with that in mind, I think we all agreed as a team we just want to have a nice friendly discussion this afternoon and bounce around some ideas and see if we can change some minds either way. So I hope you all enjoy the next hour and a half or so.
Thank you, Chris. What we're going to do is the levels are going to be set throughout the actual the debate, because we've got 3 mics on at the same time. It's very hard for the technical team. And can I just mention that the technical team have had a horrendous job to get this sorted over the whole 3 days, and they've put in a lot of effort. And I don't know if you've seen their hardware, but it's actually quite incredible. So anyway, I'm going to introduce Tom for you. But one thing I can say, the guys that I gave the eggs to, can you just make sure that they're not looking when you throw them? So if you could do that for me. So anyway, I'm going to hand you over to Tom.
Hi everyone, my name's Tom, please not the eyes, Williams, for those throwing the eggs later. And I feel a little bit too short for this microphone, but good. Yeah.
Believe in it.
So yeah, thanks for having me along this afternoon, and I hope that you'll enjoy the next hour and a half. I hope we can provide some kind of challenging viewpoints, and you can provide some challenging viewpoints to us. So to introduce myself, my name's Tom Williams. I'm a second-year PhD student now, down in Cardiff University, and the Earth is a little bit close for me. I'm actually an extragalactic astronomer, so I've been looking at galaxies beyond our own Milky Way and modelling the light that goes through them and how that interacts with other parts of the galaxies. So the galaxy I'm working on is about 800 kiloparsecs away, so I'm looking at scales of kind of unfathomable to humans, I think, but actually quite nearby for astronomy. So I've had the kind of honour, the privilege of being sent off to Hawaii twice now in the last year to go observing. So the first time I went in, I was actually there at Christmas. I landed on Christmas Day. The second time was last September, and one thing I've heard quite a lot while I've been here today is that you should maybe not believe what people say at face value and trust your own eyes. And kind of with the stuff that I do, I'm very fortunate that actually I can do that. My galaxy is so close, it's about a square degree on the sky, so about the size of a full moon, but much fainter. So you can actually see it with your naked eye on top of Mauna Kea if you've got good visibility, or if you have kind of like any reasonable telescope, you'll be able to see it. And so I could see this thing passing over me during the night, which I believe flat Earth theory can explain with the rotation of the celestial sphere. But what I noticed was that when I went out at Christmas and when I went out in September, was that this object was rising and setting at different times in the night, which I don't think. This is my question to you, I guess. But this can be explained by the Earth's movement around the sun. So yeah, I am a believer in the globe. I'd say not because I was taught it at school, but I've kind of critically evaluated it past there. We've heard about Eratosthenes earlier today, but I'd like to bring up someone who wasn't a scientist. He was a 14th century friar called William of Ockham. So you might not have heard of him, but you might be familiar with the principle of Occam's razor, which basically states that the more assumptions you have to put into something, the less likely it is to be true. And I think that's ultimately why I believe in the heliocentric universe, that the Earth is a sphere moving around the sun, because it quite neatly explains day and.
You've got a fan out there.
Yeah. Oh, yeah. My number one fan did say he'd be late and that I should wait up.
Thanks, Bob.
Yeah, someone has to support me, I guess. But yeah. The Earth moving around the sun can quite neatly explain seasons and day and night, and the theory of gravity explains why we're not all floating off into the void and what keeps our atmosphere here. And so they're quite simple concepts in principle, but quite demanding mathematically, which I think is interesting, I guess, that these things can have such a simple idea. If I throw something up, it comes back down. This is obvious to everyone in the room, but yeah, and that's those kind of simple observations of the everyday world are why I believe in the globe and why you guys believe in the flat Earth. So kind of science, there's a kernel at the centre of science that says that we demand that you be logical. And so I think that is like a very important thing to keep in mind kind of in the next hour and a half, and after we leave this room and go back to our normal regular lives after this. So I think I've probably whittled on for a bit too long, but I'd just like to finish by saying thanks for inviting me again, and I hope you really enjoy this debate, although I'd like to call it a discussion, because it sounds a bit less aggressive. But thank you.
Thank you, Tom. I'm now going to introduce to you Luke, and thanks for the 22 minutes. That's good. Up to you.
Yeah. Okay, so if this was too short for Tom, it's definitely too short for me. But yeah, can we actually adjust that? Thank you. All right, so hello everyone. My name's Luke Johnson. I'm a first-year astrophysics PhD student at Imperial College, and what I do is develop stellar variability simulations for exoplanet surveys. And now a quick overview of this is that exoplanets are planets outside our solar system. Yeah, nice, yeah, that'll work, yeah. Yeah, that's fine, man, that's fine, thank you. Is it, yeah? I'm scared to touch that.
Is that okay?
Okay, yeah, I won't touch it, I swear. Okay?
Do anything to upset them.
Yeah, that's perfect, man, thank you very much. Okay, so basically, a quick overview of that is that exoplanets are planets outside our solar system, orbiting a star other than our sun. Now, we'd love to look at these planets and learn more about them, but as they're such dim objects orbiting distant bright stars, we have to use indirect methods to do this, such as looking at the light from their host stars. But this presents a problem, as stars are not stable light sources. Well, you know from the nursery rhyme, they twinkle. So this is due to surface features such as cool star spots and hot active regions. And the noise these can introduce can actually mask the planet's signatures in that light. So this is why I developed my simulations, to try and quantify and understand that noise, so hopefully it can be removed from those measurements so we can see these planets. Okay, and I won't go any further into that, but please ask me more if you want to hear more later. So as you probably guessed more that, I believe that the Earth is a sphere, rotating on its axis as it orbits our sun. I believe this planetary system, while unique as far as we know due to the presence of intelligent life, is one of hundreds of millions that make up our galaxy, the Milky Way, and that the Milky Way is one of countless galaxies in a universe that, as far as we can tell, has no bounds. Now, I believe this not because it's what I was taught in school, but because what I was taught in school aligns with my own experiences and the things I see. Simply put, the current model answers all the questions I have about the world around me. For example, why gravity can be tested for on a micro scale, such as in the Cavendish experiment. And, and why last summer, when I stood at the peak of Kilimanjaro, I could not see the ocean past the edge of the continent. And why my professors, who are some of the most perceptive and skeptical people I've ever met, could dedicate their lives to analysing data from space observatories if that data is all being faked. It just personally doesn't make sense to me. Now, I didn't come here trying to change anyone's belief set in an afternoon. And what I'd actually like to urge you all to do is exactly the same as what I've heard from flat earth speakers many times over, which is to be a skeptic and to do some research. But there are pitfalls to watch out for in that, basically. See, while scientific skepticism is healthy and constructive, denialism is the opposite and all too easy to mistake for the other. See, while skepticism teaches that evidence is worthy of belief if an observation can be repeated under controlled conditions, denialism teaches that evidence, no matter how reproducible, can always be rejected out of hand. And now some people, when challenged, will tend to revert back to their core tenets or beliefs, such as, the Earth, like the horizon, looks straight to me. It doesn't feel like the Earth's moving beneath my feet. My senses tell me that the Earth is flat. And now some people would demand answers to apparent holes in spherical Earth theory, implying that they'd come around if those questions could be answered. But I mean, this is why we're here today, to try and answer as many of those questions as possible. But there are some people who, even if all their questions are answered, will not consider the alternative because they don't want to consider the alternative. And that is denialism, and it is not scientific in the slightest. So the second pitfall to watch out for, and this will be my final point, is in actually conducting your research. See, we live in an age of misinformation where anyone can cobble together like an image or blog post or video with misleading or false information. And you see this all the time. These are techniques employed by political extremists on every side, basically. So when researching, red flags that you want to look out for, lacking evidence, lacking support, like lacking methodology to claims, basically. So say if someone's done a calculation, we want to know where they pulled the numbers they put in from, basically. No references or citations, another big red flag. And also confusing perspectives in video and picture evidence, and a clear bias from the content creator. So basically, don't rely on YouTubers and bloggers. Google is your friend. Okay, and that's everything I have to say. Thank you very much, guys.
I'm now going to pass you on to George. Thank you, George.
Hi everyone. I'd first like to say that we're really happy to be here today, because it's very easy to stay in your own little bubble and not realise there's other views out there. And that's for us as well. You don't learn anything until you hear another viewpoint. So we hope to learn how you lot think, and hopefully you can learn how we can think. And I like to see this as a discussion, and I say that because with a debate, you can easily win a debate without having the facts behind you. Otherwise, we wouldn't have politicians and we wouldn't have lawyers. So hopefully we can see this as a discussion and just put ideas ahead instead of necessarily seeing this as one side beating the other. I'm a first-year PhD astrophysicist, which means I'm not an expert and I'm definitely not a scientist, not yet. If anything, I probably know less now than when I started 8 months ago. What it does mean, though, is that I'm a trainee scientist. And what that's given me is a load of skepticism. Every day I have to go to work and spend 8 or 9 hours trying to work out what's wrong with what I've done, disprove my own work, find out that this magical new discovery I've made is actually just an error in a line of code. And I do this every day, and it's horrible. But you do it. And you do it because that's how we find the truth. That's how we find the real discoveries, and that's how we go forward. And hopefully we can get some of that skepticism across now and give you an idea just how rigorous we have to be before we can go from initial data to new discovery. Now, the actual area I work in is dark matter. And the reason I bring up dark matter is because on the surface, it sounds like a lawyer's attempt to explain away the fact that there's some evidence against gravity. But that's on the surface. Really, it sounds quite fictitious. it sounds like a conspiracy theory, and yet this is the side that science supports. And that's because we have some hard evidence for it now. And hopefully today, at some point, I'll be able to discuss why the idea of dark matter, which sounds terrible when you first hear of it, can actually be supported where, say, other ideas aren't, because the evidence isn't there. Hopefully I've kept it quite brief, and we can have a wonderful time today. So, there you go.
Tech team, if you can put on the left mic, please, for the flat earthers. I've just had a chat with Darren, and we decided, if you guys are okay with it, is because there's so much juicy information you just put in there, it seems silly to go straight to the questions and overlook some of the things you said. So if you're okay with this, we would. Going to field those questions as well. What we'd like to do is no. What we want to do is what you've all said. There's some really powerful information. So what we did is when we first produced the questions and run it by everyone, it's because at that time we had no content. Now we have content. And I feel, and hopefully everyone in the room feels the same way, that this is such a golden opportunity to actually not address, but comment on. Now what I think, I don't know if this is going to work right, but if we ask a question, you do a rebuttal, we'll obviously kind of get back with another rebuttal and you're going to do a final one, and I think then that's when the question should end, unless it really shows that it's got legs that we need to continue, because what we want to try and do is cover a broad spectrum, but at the same time we do not want to be skipping over a question and not taking it far enough that we end up missing a good point. The one thing I would like to mention about Google is, and there's nothing about me, I just want to mention it because it's something I researched about the Orion's Belt, is that when I looked up the Orion's Belt distances from Earth, Google, Wikipedia and NASA all gave different distances. I'm not going to swear, but I think that's bollocks. So anyway, you please. I want the same cheer you gave Iru. Okay, no, we're going to go because you said. I can address this one. Do we have this one? No, come up, because this is going to be fun. We're going to be very fluid on this, guys.
So yeah, Orion's Belt is a constellation in our Milky Way, and we don't really have a very good handle on distances in the Milky Way because, yeah, this is why I work in extragalactic astronomy, where we do know distances. So the problem is, so you have your Milky Way. It's got say a black hole at the centre, and it's got these spiral arms coming out from it, and you're looking through both of these spiral arms as you go to things. So if you want to measure the distance to anything, there are two that you can measure, essentially, one going through like the near side and one going through the far side. So yeah, we really don't have a handle on distances in the Milky Way at the moment. Like, ask me how many spiral arms the Milky Way has, nobody knows. Stuff like that. Extragalactic astronomy is way less messy, promise.
Okay, thank you very much. Okay, what we're going to do, we're going to hand over to the Flat Earth team now, because there's bound to be some juicy bits in there they would like to cover. So hopefully the mic is live. So if you'd like to give it a try. No, we've got the microphone there.
Okay.
Yeah. Sorry.
Okay, hi guys, nice to meet you. I was just writing some notes down, just some of the things you said. I'm not going to go into a lot of detail, but just to rebut a lot of things you said. I know that people in here were thinking, no. So I'll just hopefully voice them for a lot of people. Then obviously Dave and everybody can say their bits that I missed. First of all, I'm sorry, I've forgotten the journalist's name who had a great speech at the start. Chris. Hi Chris, thanks. You actually said something interesting. You said something about we make observations and then we get theories and then we get the facts. I picked up on that straight away. Shouldn't the last two be the other way around? We make observations. If they're repeated observations and they are verified, that then makes them facts, and then we can then we develop the theory from the facts. You actually said it the other way around, and we find that that's what the heliocentric theory does a lot of. They've got the theory first, and then they try to get the facts. Okay, I'm just going to pick up on your points. Tom, with your modelling, how do you know the scales and the distances? And again, you can obviously rebut this at some point. How do you know that those scales and distances are correct? What we have rejected is the vast universe, is this the idea that stars are just huge and we're living in this great big vast universe and the distances are vast. Tycho Brahe, that was the main reason why he rejected Copernicus's initial idea, because he had watched he was the premier astronomer in Europe, and he'd watched the heavens for a long time. And he obviously never noticed any parallax. Now, I've done a little study into parallax. It was Frederick Bessel in the late 18th century, or was it the 18th century, who first ever measured parallax. But what astronomers always do is they remove the negative parallax results. So, the bottom line is, we don't accept these distances are so huge. We think there is a way of doing dual astronomy, so that we think the stars and the galaxies and everything else are very, very close and very, very small, and you will still get the same mathematical results and the same observations. I think, again, you're starting with a theory, getting the numbers, and then saying that proves it. I think there's two ways of explaining it. I think there's a dual way of explaining it. You also mentioned about some of the phenomenon that you see, and you're assuming that everybody here subscribes to the one-pole dome model. I know that's the main flat Earth model that you've seen, the circle with the dome and the North Pole at the centre. I completely reject that. Most people in this room know I completely reject that. I'm not the only person that does that. I believe, because of astronomical observations, that we have a two-poled sky. There's a celestial sky. The Earth is still a fixed plane, but the stars, well, the heavens are two-poled and they roll over two poles. Okay, so if the atmosphere, I'm sure everybody will agree with this question, if the atmosphere is kept in by gravity, how come a helium balloon, how come it can't hold of a helium balloon? I'm sure you've got a great answer for that one. Luke, on the screen behind you, you do exoplanets. Yes, most of our information for exoplanets comes from the Kepler telescope, I believe. Okay, a lot of it does. It was commissioned in what year? 2009. Okay, and I'm sure there's more than this now, but in 6 years, it's managed to spot 4,000 exoplanets, which is basically, let's face it, a little or a regular dinking light, as of a distant star.
There are actually a lot of different detection methods.
Yeah, for sure.
Can I just say?
Okay.
Am I meant to be talking about now?
No, okay. So don't worry about it.
I'll let you just keep going.
Yeah, fair enough. Yeah. So you did say it's just a discussion, so you know what I mean.
Yeah.
Just two blokes in a pub. My basic question is, thousands and thousands of exoplanets in such a short amount of time. And again, real science. If I believed in this, I would want to see. And some of these orbits are 3 years, 2-3 years. So, you'd want to see it orbit 2, 3, 4 times to make sure it was a regular, steady orbit, make sure it definitely was an exoplanet. But they've found so many. This one particular telescope has found, and it's the one we hear about in the news all the time from our friends at NASA. It's found thousands. How has it managed to do so many? You know what I mean? And actually be accurate. I've talked about the dual astronomy. George, you talked about. No, it wasn't. So it was still Luke. You talked about sources of truth. Don't trust people on YouTube. Don't trust bloggers. Don't trust independent people who are doing their own research. Don't even just don't trust YouTube, but just trust Google and trust Wikipedia. What you're basically doing there is telling us to trust the mainstream sources of truth, the academic institutions which we know have distorted and perverted the truth. Which and at the end of the day, nearly every great discovery or great invention has always been by somebody not connected to the mainstream, somebody working on their own or a small team working on their own. If everybody goes along with what with what the mainstream always says, then we're never going to make those breakthroughs and discoveries and get creative as well. So I say the exact opposite. I'm not saying distrust the Google or distrust Wikipedia, absolutely, because sometimes it is actually right. You know what I mean? It is verifiable evidence. But when it comes to certainly a debate that has raised, this is the longest and most important debate in history. It's been going on for thousands of years. Those people who think it's a CIA psyop that's all of a sudden come about, it's been going on for years. in 1969, when they pretended to go to the moon, and then in 1972, when they showed us shots of the Earth, the debate died down a bit. Now we've got the internet and mass communication, and we can get those independent sources of truth, and we're not reliant just on the mainstream television and mainstream newspapers. Now we can actually discuss and share information, think for ourselves and say, you know, I'm not going to choose that model. They might both work mathematically or observationally, but I'm choosing this model because it actually, you know, it also fits in with my own senses as well. So I say the opposite. I say not trust independent research, but absolutely use all sources. And I personally, just, you know, having seen false flags and all the lies on mainstream information, I'm more likely to distrust the mainstream information. I know that goes for most people in the room. And that's pretty much it. George, I'll just say, I don't know, do you know about the electric plasma universe? Do you know about the Thunderbolts project?
I had to dig through their wiki page, but not for long.
Okay. Just saying that, again, I would imagine that a lot of people in this room and a lot of people out there, it's been around for 100 years, it's not a new thing. They reject Einstein, they reject the theory of relativity and gravity. The sun is an electrical conduit. You know, we live in an electromagnetic universe. It's another alternative. I don't know that much about it, I can't go into deep into it. I would imagine Iru knows a lot more about it than me. But again, there is another scientific alternative explanation to what you guys have been taught. That's it for me. I'll pass it on.
Hiya, I already met you guys, so hello again. Well, Darren's basically usurped all the questions I had anyways. I won't speak again after this. But there was a couple of little points. Yeah, you said like, was it, what's your first name? Tom. You said about stars being 10 parsecs away. Is that like 150 miles, something like that? I don't know, I mean...
No, that's parsecs.
Oh, right, yeah, something like that.
It's about 10 to the 30-ish.
10:30? So, no, right, no, it's okay.
30 metres.
Right. Okay, I'm just saying, it's like, that's gibberish to me. So, parsec, okay. Yeah, but...
Makes your head spin.
It does. Now, somebody else said about Occam's razor, and obviously the Bohr model, you know, fits Occam's razor, and you know it's the simplest. No, the simplest explanation is our senses are right. That's the simplest. Have you looked at? You know, Principia Mathematica? You know, that big book from Newton explaining gravity, or the theory of relativity. You know, that's not simple. It's a complicated argument to prove a concept. What's going on back there? Yeah, but what I'm saying is a complicated principle to try and prove this concept that isn't workable. Yeah, the simplest explanation tends to be the truth, and the simplest explanation is that when we look at the sea, it's flat. When we rely on our senses, our sense of balance, our sense of acceleration, yeah. We don't feel like we're moving. We get senses to help us navigate this world. And we damn well better have accurate information. Right? Yeah. So yeah, I'm just saying that, yeah. I'm just saying that, you know, the simplest explanation is that the Earth is flat. You also mentioned about gravity and linking it to you know these theories. Well, the tendency of something to fall when you let go of it is independent of gravity. Gravity is just a theory to try and account for it. Okay, and which type of gravity you're talking about? It's like we've got two flavors. Yeah, some kind of mysterious force between two things, or some kind of curvature of something called space-time. Yeah, neither of them work, right? But they're independent of this. You know, I'm going to do a Neil deGrasse Tyson. No, I'm not really. All right, not really. But I'm just saying they're independent of this tendency for something that you let go of to fall down to the ground. Yeah, it's one of those confusing arguments, right? So I haven't got very much to say. Darren took the limelight.
Hello. Oh, that was loud, wasn't it? Hopefully that's not so bad now. Can everybody hear me okay? Yeah? Hi, my name's Sean, School of Life. How are you doing? Nice to meet you all. I believe at the beginning you mentioned the scientific method. I believe that's right, isn't it? You would all attest that you confirm to the scientific method. Would that be fair to say in your various fields? Yeah. There's a fundamental flaw with that, isn't there? Because in 2015, people who you would consider not just professors, but at the very top of your field all came together, didn't they, in Zurich? I think you'd probably be aware of this, to discuss this very thing. And they said, actually, that to defend the integrity of physics, that's what the scientific method does. And that's a huge flaw, actually, in all of your debates. It's untestable, attempts to address the fundamental questions concerning space, matter, time, and all those various things that you love. And that's the biggest flaw. And I've got nothing more to add except one point. Luke. Sorry, hi, Luke. No, yeah, I'm not picking on you. I liked what you said, but you kind of missed a very key point. You sort of suggested that people have a deniability about them, and in a way that you phrased it. And I just wanted to just bring you back on point, if I may. People don't start off at flat Earth. They have the gravity, they have the globe, and everything else thrust upon them. It takes an awful lot of independent research, actually, to reach a conclusion which is not mainstreamly popular, to actually talk to people openly about your belief system, which is strange when you think about it, and I touched on this yesterday. So I just wanted to make sure that you're aware that you don't start off with deniability. You have to eventually grow to realise that something is fundamentally flawed. So I just wanted to raise those points and keep it simple. Thank you.
Well, hello guys, nice to meet you. I come from Argentina. So really nice things that you say. Maybe I understand the 80%, but I'm going to try to make my best. Really, I believe this is a nice situation that we live in today, because we ask for this to be happen. I mean, just have a friendly speech between some different point of view. I believe nobody here has the equipment of the knowledge to really combine some other peoples who believe what believe or in what must be believed. I think that this is a personal process. Depends of the sources. I believe what something important is I think the difference between flat earthers and heliocentric models is that we came from that world. I mean, we have all the same, educational system, so not maybe so deeply as when you enter in university to study, a specific situation about the astrophysics things, but we know the basics, and a lot of assumptions that then go deeply in universities are based in those simplest, observations, and we have that, base knowledge inside us, but we open to achieve the other part of the history. And maybe a lot of heliocentricists out there, they reject that point of view. I don't say you are doing that, but I mean, they don't take the time, enough time to research, not from YouTube, because, I mean, a lot of YouTubers that speak about flat Earth, they take the information from books and from other scientists. I mean, Thunderbolt Project, maybe there are a lot of scientist team out there. It's not just a YouTube channel. They gave their names, they gave where they study, and they start challenging because, for example, the thermonuclear sun, there are a lot of things that nobody can explain and don't have any sense, and when you think in electrical sun, it become more understandable. But those guys are astrophysicists too, or are engineering. I mean, they are not YouTubers. They go from coast to coast on Europe, making conference talking about this and challenging these kinds of concepts. Every flat earther out there start with Samuel Roboham book. I mean, he was also a scientist and a mathematician, and with the nickname Parallax. So that guy is an awesome guy. I mean, for his time, what he do is amazing. In fact, I don't think that he is totally incorrect in his assumptions or method to understand the world that surround him at that time. In fact, he was very persecuted at that time. We have William Carpenter, we have, of course, ancient civilization that nobody can believe that if you build that kind of structure as pyramids or all the celestial behavior that we use today, like eclipses predictions, although the constellation that we see in the sky, the name even of that constellations, that things come from the ancient guys. I mean, they don't. I don't think that guys are so awesome to build that things, calculate eclipses, calculate the weather times, when to grow food, when celestial behaviors, and they are full to don't understand the surface where they live. I mean, for me, that is, the typically joke about flat Earth is, hey, you are under the turtle with elephants. And I ask the same question when an astrophysicist see a constellation, and I say, where is the lion constellation? Where is the lion up there? I mean, there are 10 points of light that you believe in those ancient culture that he draw this depiction of the lion in that constellation to understand or to tell a story, want to passing generation stories. And sometimes a lot of heliocentrics, they don't take this time, which is required a lot. How many times we spend in school, receiving this information? Years after years, like 20 years before enter into university with this bias concept about the heliocentric time. So if you don't take at least I don't say full time 8-10 hours daily basis studying flat Earth, but at least you need to wait like I recommend like 3-4 years at least. That was my process to incorporate the other part of the history to try to balance and say, because we need to recognize that there is a lot of observation that the heliocentric model can explain but can't prove. And it's not what you know, is what you can prove. Because I can explain how, before I talk with this guy, I can prove how unicorn fly because it has wings. But show me the unicorn. It's a little bit. I mean, how you explain that the water, that all we know in mechanics fluid seek its level, turn into a curve. I mean, what is the scale of that? I mean, what is the scale to replicate that on lab? Because somebody say no, because the Earth is so big and the attractions to the center of the Earth is what caused that the water curve. Okay, we see all the oceans flat, which is a really great scale, huge scale that. So in flat earther, we say, okay, if I go into this scale, for example, and I make a mountain and I drop water here, that water is going to go and seek its level. At this scale, at world scale, is going to all the time happen the same. But in the heliocentric model, how you prove that the water stick to the outside of the container, at what scale that start happen? It cannot happen at world scale, because you need to have this microcosmos observation also, a microcosmos observation. So that for me is a huge red flag to trying to, you cannot prove that the Earth is a sphere just for observing and doing math on celestial things that you're never going to achieve to observe, really, from outside this model. We need to lead with atmospheric refraction, apparent positions, who, in official science, who saw the parallel rays of the sun. I don't ever see something like that. I good research about that. Some pictures show that, taken from a plane, show some parallel rise, but why you see parallel rise in those pictures? Because the picture is taken with a zoom. So they only show this part of the picture. When you start to extend it, you're going to see that rays come here, and they just show this part. So nobody see parallel rise. And all this nonsense of the globe world start in that time with Eratosthenes, that one day he woke up and said, okay, the sun had that distance and the rays are parallel. I don't know if you in the university teach, yeah.
Sorry, what's your question?
No, I just make my presentation. Okay, something I'm gonna, okay.
We need to give them a go.
We need to make our question now? Okay. Sorry guys. Okay, I mean, there is a lot of things that not just, I believe that you can prove just the spherical model based on celestial observations. I believe that it's more important to, understanding where we put our feet before start make assumptions in other, some distance object out there. And I believe that the parallel rays, the cold water, the distance to the sun that was changed like 5 times. Copernicus says 3 millions, Kepler says 12 millions, so on and so forth. I mean, all those guys make calculation based on a sun at 3 million miles away. They come Kepler say, no, it's 12 million. Then come other one and say, no, it's 25 million, until our day that we believe is 93 million miles away. So I'm going to come, because if not, I'm going to be killed. So one of my questions is, at what scale we can prove that the water start curve and be stick outside of container? That is my question. Thank you. Sorry for the time.
While I'm waiting, I don't think they need the questions. Thing is, that looked real, but I think it was fake. I think that's Elon's first draft on what he should have said. Okay, we're going to have to set some ground rules here, guys. If you ask a question or you mention something, I mean, unfortunately, or fortunately, actually, because I think this is brilliant, is you've made a statement, or where you are, you've rebutted. What we can't do is spend half an hour coming back. What we need to do is it has to be within 90 seconds, unless it's a really salient point. Yeah. So I'm not the tallest in the room, but I'm pretty tall. So anyway, so what I'm going to do is we have to give these guys a very fair chance, because if this is not done with integrity, it's pointless. So I think these guys need to have a chance to come back. I was actually writing that line at 4:30 this morning. So, so anyway, I'm going to pass over to these guys. If we can have the microphone on for them, please. But I am going to try, and we've got to try and. I think it's gone off. I think we need to try and stick within a very small window for everything, to have everyone to have a chance. Because obviously there's 4 guys on this side, there's 3 on this side, and I think if we do not set this out right, it's not going to have as much value as it could be. So anyway, over to you guys.
Oh, it's working now? Brilliant. I heard 3 words over there that worries me. And it really should worry you, everyone here. Just a theory. If you hear the words, it's better, right? If you hear the words just a theory, this is the rhetoric of evolution denies. This is the rhetoric of science denies. This is the rhetoric. Okay. This is the rhetoric. Yeah. This is the rhetoric of people who do not understand basic science, and that's important for everyone here. So, because just a theory is not just an idea. A theory is an idea backed by evidence that has predictive value. It means you can write it down, explain what we can see, and then use it to find something nobody knows. The idea of Newton's gravity isn't just that you drop a ball and it hits the ground. It's that he could use his equations to predict where planets would be. That's what makes it special. Now, mentioned on that side was the idea of, I understand this concept of science is all not mainstream, it's on its own, it doesn't let outsiders get involved. But this is fundamentally wrong on quite a deep level. And the biggest one you can use is Einstein himself. Einstein came up with an idea that goes against Newton. It goes against our ideas of gravity. And yet the science community accepted it almost immediately. Why? Because it was better. It was better at predicting things than what came before. The perfect example is the precession of Mercury. The orbit of Mercury is not what Newton would predict. It follows a different pattern. In fact, it doesn't even follow a single orbit. It continually changes. That is not possible in Newton's gravity, but it's possible in Einstein's. So don't follow this idea that science is in its own little bubble and it's just doing its thing and not letting new ideas in. Science would not exist without new ideas. But it's new ideas based on evidence, it's new ideas with predictive value, and it's ideas with utility. Utility that makes this room work, utility that lets you drive your car, and utility that lets you use a GPS system. So I want you to all keep that in mind whenever you're hearing certain things said. Okay.
Cool. I won't talk for too long. I think something you might have missed out, I think, that when Einstein came up with his theory of gravity, he wasn't actually a scientist at all. I think he was working in a stamp office or something. So if you are... Yeah, independent researcher, very much. Just one quick one, because I think we're limited to 90 seconds now. In terms of measuring the distances to things, there are a whole bunch of ways. Common one in extragalactic astronomy is so different molecules will emit light at different wavelengths. And so neutral atomic hydrogen emits very strongly at 21 centimeters. So if you look at these things and you measure this peak, you can see how much it's away from 21 centimeters by, and then taking into account kind of Hubble's law, you can turn that pretty easily into a distance from its redshift. Kind of in our own Milky Way, it was last week actually that Gaia had its second data release, so it's very accurately measured the position of, I think, 1 billion stars using the parallax. So it's just been scanning the sky for a while, and it's looked at these tiny, tiny changes. And so because you know the angle that these things are changing by, you can measure the distance to them very accurately. But there are a whole bunch of ways to do it. You can do it from supernova going off and things as well. And these methods agree to, within 10% or so of the distance of M33. One other thing I'd quickly like to add is it's something that's been mentioned quite a lot actually this morning, this idea of proofs. I'm very much one who doesn't subscribe to the idea of proof. I think a theory is just a theory until someone comes along and proves us better, which is what Einstein did for Newton, for instance. I don't think anything is ever, like we can never prove anything with 100% certainty. I think that's something we can all agree on, and it's a very important part of skepticism, I guess. But I'll leave it there.
Thank God I had questions I didn't rip up, because we are there. Thank you very much, guys, and thank you. Hopefully you're all enjoying it, because sitting back here, I'm finding this a lot of fun. Okay, number one question is to do with curvature. And I'm not saying that we've actually got the right questions or the way we present them is correct. All I've done is I'm just a normal flat earther who's very limited knowledge. And between Didi and I, and we spoke to the boys, and we went back to these guys, we tried to come up with something that gives us a range. So some people are going to criticise it because we just can't get it right for everyone, but we just done our best. So anyway, question number one is, why doesn't the artificial horizon on a plane roll backwards during straight and level flight? So over to you, boys.
Thank you. So this is terrifying. Okay. So basically, the main thing to take from that is straight and level flight. What is meant by straight and level flight? Because I imagine when a pilot's in his cabin or an onboard computer's doing it, they try and maintain a constant altitude. Would you agree? Yeah? Yes, they try and maintain a constant altitude. So, so that's going to be determined by the dial reading on their console. So while on small scales, their flight path seems indistinguishable from like a straight line, it's actually going to be, on larger scales, curved, much like the Earth is curved on larger scales. Yeah?
What? That was the answer.
Yeah. Sorry, what didn't you get?
Can we have this mic on? Can we have both mics on? Thank you. So what you're saying is, again, on most of these answers, you seem to be assuming every time a priori that we live on a ball, and
Saying as a thought experiment, imagine we're living on a ball, and
right,
that's how it
but
would work.
but the actual facts are that a plane flies. It obviously once it's reached its cruising altitude, it flies level, and the artificial horizon doesn't dip. It doesn't have to dip its nose down every minute or so to follow the curve. What you're doing is assuming a priori every time that we live on a ball, and like I said with Tom, you're assuming that that the stars or planets have huge distances, even though what you're measuring is correct, and that obviously that you are measuring changes, you are making these observations. You're assuming always a priori that we live in the heliocentric system. If we assume, with the flights and with the stars and the measuring the distances, if we assume that we're in a small universe and that the plane is flying level over a level plane, we're still going to get the same results. And in terms of the artificial horizon, that is exactly what we observe. It doesn't roll over as it rolls over the curve.
Sorry, am I back on? Yeah. Okay. Yeah. Sorry. I thought it was a question, as in like, I don't understand how your model, the currently accepted model, can explain why the artificial horizon doesn't roll back, and that is the explanation why. In our current model, that is why the artificial horizon doesn't roll back during what you'd call straight and level flight.
Okay.
Because maintaining a constant altitude around a massive circular surface is going to be curved itself.
Calm down.
Yeah, it's not. I'm not assuming our theory's right per se in this. Yeah.
Breathe.
Yeah, I'm.
Breathe. Down.
Yeah.
Breathe. Okay.
Like that's how we explain it with our model. How do you explain it with yours?
Well, no. I think he's slightly misunderstanding the question. Okay. Yeah. Right. Imagine a plane before it takes off. Yeah. It's got a gyroscope in the artificial horizon, okay? It spins that gyroscope up to get the reference of the ground, okay? Now, if that plane starts going over the curve of the horizon, yeah, the gyroscope will stay upright as it goes around the curve, yeah, because a gyroscope has rigidity in space. It's not got reference to the Earth or gravity or anything. It's rigid in space. So it will stay upright as the plane rounds the curve of the Earth. So the artificial horizon will roll backwards. Yeah? Will appear to roll backwards in the plane. But it doesn't. It stays straight and level, indicating that the plane is not going over a curve, but flying over a plane. That's what the question is.
Of gravity or anything like that, if it relies on the horizon?
No, it doesn't rely on any horizon. It's rigid in space.
Rigid
in
space.
That's one of the properties of.
Yeah, I don't think it's unaffected by gravity. I mean, I'd have to check that. Like
your own model says rigidity in space is unaffected by gravity or wherever it is on Earth.
Do you want to? Yeah, I can. Yeah. Go.
Yeah. So I must admit that I'm not an expert in gyroscopes, but I do have one at home, and I was always under the impression that the gyroscope self-righted. So you spin your gyroscope, and then whatever angle it is, it'll end up pointing upwards.
No.
Is that
rigidity in space means once that gyroscope is spinning, it will stay in its orientation, and resist any attempts to change its orientation. It's not affected by the center of the Earth or gravity or anything else. It's rigid in space.
I'll just add that we've actually got a gyro here and we will demonstrate it.
Yeah.
I will also add, as Rob Durham in here has a video there where he spins up his high precision electric gyroscope, right, and sets it on a surface and videos it for 6 hours. Now, in 6 hours, the Earth would have moved something like what, 90 degrees. Okay, so that gyroscope should have moved in that time because it's rigid in space, but it doesn't move, indicating the Earth isn't moving.
I don't know enough about gyroscopes to rebut that, so I guess we'll move on to the next question.
I'll just add, out of all the questions in my video about all these different proofs, that question nobody's ever been able to answer, because they always come up with this idea that the Earth affects it, or we have some kind of mechanism to right the gyroscope.
Yeah.
Nobody can answer it. So
I've never been in a plane cabin.
Yeah.
So
We're sorry we can't give a good answer, but invite us back next year, and we'll have something for you.
Gotta be honest. The weekend that we've had and the stress next year, I honestly reckon that if I do that, I will have no fringe. So, can I? This is grade 1. I've got to be honest, guys. This is amazing. I don't know. Can I just get some feedback from the audience? Okay, we're live streaming people as well, but we can't get that. What are you guys? Can I just take a 2-second? Is it 1 or 2 people that can comment about how this is coming across to you?
Brilliant.
Yeah.
I think it's very professional.
Well, yeah, that's me. What about these guys? Microphone. And can I just mention, while Dee's running around, I have to be a mediator here, and I have to be impartial. So what will happen is I will make sure I look after these guys because I have to. So even though I mentioned about the gyro, it's only because I know what's coming up on the programme. But guys, you're safe with me. Okay, we've now got Nora. I'm just doing this as a little break for the speakers to actually get some feedback from you guys. But Nora, if you can do yours.
Thanks. Oh, I've never spoken on a microphone. Anyway, I'd just like to make a comment that all this time that I've been in the Flat Earth movement, one of my biggest interests was to find more dialogue. So I think it's very laudable that you've had this, and I think it's an excellent moment of progress for
Thank
us.
you.
And yeah, where you have a true dialogue between the two camps, because they don't seem to have enough contact between each other, despite what you say that you are connecting with the public. I don't think that's true. I know many PhDs, they don't connect, but I think that it's indicative from perhaps a few of the answers we've had, especially the young man who you weren't familiar about the gyroscope, and I find that it's indicative of a lack of preparation. But it's indicative of a lack of preparation. These are basic tenets of science, but I feel like you haven't fully examined the questions to come to a debate like this. That's all.
Don't worry, I'm going to defend you on that. Okay, can I just say that I like Nora and I think you're great, but I have to defend these guys on this one. How could they actually look into everything to be prepared? They can't. So even though I think it's a cracking point, it isn't fair on these guys because no. I must admit she's a troublemaker. It's Dee, if you can. But
A fraction of our age, and they haven't had time to do all the research they've done.
that's why I was hoping to do this next week, to give them another week. So, now, even though you guys haven't come across a gyro, what I would like is for when you see the demonstration of the gyro is for you to scratch your head and wonder why, because we have, the thing is about us, and we're lucky, and I've got my impartial hat on still, we're lucky that we look at so many things and so much research, and that we're questioning everything, and sometimes we don't understand it, and sometimes we do understand it, or we think we understand it, or maybe we do, I don't know. But you guys, you've all got your specialist field, so you're not going to have your specialist field and research the gyro. You're not going to have your specialist field and make sure you know how popcorn's made, because it isn't something that's important to you because you're doing your specialist subject. I recognise that. So we have to try and look after these guys, that we are looking on point for what they're actually about. If we find that this is a very powerful hour and a half, then we can actually roll it out. And can I just say, I really appreciate these guys and Chris for actually being here, because I was told that no one would actually bother or could do it. These guys are here. you want to say something?
Yes, I may.
Yeah. Go to the microphone, please.
Is it back on? Can you hear me? Yeah. Yeah, just while you go away and do the research on the gyroscope, there's an even easier way to find out about this. Just ask pilots, just for your information. Thank you.
I disagree with that as well. Because a pilot doesn't know. They just accept what they're given. No, I agree. No, I was making a point. Sorry. I'm not going to get that point tonight. Oh, by the way, have I mentioned it that I actually drink Stella? So, anyway, if everyone's okay, I'm going to move on to question 2. Yeah? Actually, it kind of was covered by Darren in reply to you earlier, so I'm not going to... Oh, well, I'll mention it and see if it's got any legs. If gravity is the only thing holding the air to the surface of the Earth against the tendency of a high-pressure system to escape to a low or negative pressure, then what air is heated and so... Oh, sorry, when air is heated and so is less affected by a gravitational pull, shouldn't it then succumb to the force exerted towards a region of negative pressure? What? No, I was joking. Because we've asked the question, I feel it should give them the chance.
No, I was going to explain if it
Yes,
was,
yeah, okay, are you happy with that?
I think so. If we obviously don't understand it, then we'll let you jump in. Okay.
Yeah?
Yeah.
Okay. Yeah, they've done research on it all, and that's fine. But yeah, Dave, comment on that.
So can we also link this one, because it is to do with buoyancy and stuff like that, can we also link it to the helium balloon?
When you got your chance to speak, you take it any way you like. If it can be hopefully on point, that'd be great.
If you transfer that, I'll do the helium balloon now. Okay, yeah.
Okay, so basically, you're asking why air can't be heated and escape, basically. Yeah? Is that what's being asked?
Yeah, it's a question that's been asked. I'm only the deliverer.
Yeah.
Yeah, the question basically is, if gravity is the only thing holding the atmosphere to the Earth, okay, and the atmosphere is right next to a vacuum.
I've got it. Cheers, Dave. Yeah, basically, there's two competing forces. There's gravity pushing downwards, and then there's a thermal pressure of air pushing upwards. And now the laws of gravity dictate that the air pressure is going to be higher at the center, nearer the Earth than outside. So if you got a heated column of air that would rise away from the Earth, it would, well, as it would rise, it will become less dense as it's less affected by the gravity, as it will be at a greater distance, and thus have a lower thermal pressure pushing upwards. So that system stays in that equilibrium state. And that's called the hydrostatic equilibrium, and you can read a lot about it.
Okay, so okay, let me get this right. Okay, so we've got an state of equilibrium.
Yeah, gravity pushing down, thermal air pressure pushing upwards.
Well, when you say thermal air pressure, what I'm seeing is you've got a vacuum next to a pressurized system. Okay, and we always see. Hang on. We always see where there's high pressure next to low pressure or zero pressure, a movement from between one and the other. Okay. All right. You say that. I can see the guy going, no. Okay. Right. Just to change it just slightly. Okay. We can do an experiment. Now this is all about doing experiments. Yeah. If we had a container, right, and we evacuated that container.
This is from your video, isn't it?
Yeah.
Yeah.
So we had a container, evacuated that container less than the vacuum of space, yeah? And we had that container down here, near the surface of the Earth, where the gravity is the strongest, and we pierced the bottom of the container. What would happen?
Okay, so the container's like, it's a vacuum inside the container.
Yes.
So when you pierce the container, air will rush in to balance that out, basically.
And it will fill it up and balance it out.
Yeah, because it'll equalize locally, basically.
So how can, on the surface where it's the gravity strongest, with a vacuum that's weaker than space, how can it work down there?
Because
and not work up there?
it's unfortunately not analogous, because it's not a really high pressure system against a really low pressure system. It's a gradient. So as it's really dense at the surface, and then that density decreases and decreases towards the vacuum of space, basically. So it's not there's no wall. at which
Okay,
there's
but
vacuum.
there has to be a boundary condition now.
Well,
there has to be a boundary condition. Otherwise, the air molecules at the top, right, the few air molecules at the top will immediately go out to space, right? They'll immediately.
Yeah, no, it's not a negative pressure system. It's an incredibly low pressure system.
We always see high pressure goes to low. Yeah. Doesn't matter if it's negative or low.
Yeah, well, yeah,
high
that's
pressure goes to low.
Yeah, unless there's forces acting on it, and that is gravity that's acting on it, keeping it
what I'm saying
on
is,
Earth.
at the top of that atmosphere, okay, there's the few atoms of oxygen or whatever. Yeah. They will succumb to that pressure going outwards to a lower pressure.
No, though, because gravity works against that thermal pressure.
Okay.
And make that local equilibrium state.
I'm sorry, but I'm just saying if those free ones at the top disappear, then you've got a lower surface, and now these ones that are free will start disappearing, and it's a cascade effect. And even if somehow you've got equilibrium with that system, as soon as the air gets heated at the top, it rises
and becomes less dense, then has less thermal pressure. So.
Okay. So
so
this thing.
That equilibrium state balances it wherever it is, and brings it back into that equilibrium. And that's why we're just losing atmosphere. Basically.
So where can we see an example of this idea of thermal pressure demonstrated on Earth?
I can't give an example right now.
Well, that means it's not repeatable.
I think it is. I think it is repeatable. I think there are experiments. I haven't written an experiment down.
If you can't repeat it, if you can't show me where this concept of thermal pressure, if you can't demonstrate it, how can we see? No, it's real.
Well, thermal pressure. You can if you have air particles in a container and then you heat the air particles, the pressure is going to increase as the temperature increases. That is thermal pressure. It's the kinetic energy of the particles and their collisions against the wall of the container. That as the temperature increases, they have more energy, more collisions, more pressure.
Yeah, what is?
Yeah, no. This is you said an example of thermal pressure.
Air pressure is by definition created within a container. You can only get air pressure in a container. So what's the container? Obviously, the earth on the bottom is going underneath. But what's your container? What's your lid to create the air pressure?
Yeah, there's no set boundary. It's that gravity holds our atmosphere to our planet.
The scientific definition of air pressure is that pressure within a container. So what is your lid?
Is it? No. Do you want to take over?
Can I just mention, guys, that we're actually going to allow the audience to ask questions at the end, and even though it's fantastic questions, we've got to be fair to these guys on how we do this.
To go on pressure there, pressure doesn't require a container, and we can give quite an easy example of this. I'm going to use the ocean for this. If you imagine we take a random part of our ocean, we're underneath, we take a random bit of water, and you make like a dotted circle, and there's a bit of ocean there. That part of ocean, assuming there's no waves and assuming there's no motion, is staying in that one place. Now, you'd think gravity would make it want to go further down, but it doesn't. It stays where it is. That's because there's an inherent pressure taking place there due to all the water surrounding it. So because of that, you can imagine if we're using arrows like a basic mechanics, you've got an arrow going down, and then you've got arrows in all other directions and an arrow going up. That's the up arrow is the pressure, and that's what's balancing it, keeping it there. Now, we can do the same for air. We can take any bit of air, make our little dotted sphere, make our dotted circle, say we talk about this bit of air, those atoms aren't moving. And they're not moving because there is a pressure pushing it outwards and gravity pushing it down. Now, I wanted to link this to the helium balloon to give an example of why it does work. If we take our helium balloon, now the helium balloon is less dense than our air. So, to get less dense than our air, that means less mass, which means less gravitational force pulling it down. You now have the same big arrows pointing up because the air pressure is the same, but now you've got a smaller down arrow of gravity, and that's why you get that lift. All these ideas can be explained with pressure and gravity in this way, and it does not require a container to do it. Yeah.
I just want to make a question, but for myself, which is, all these from the early 50s until our days, the space agency launches a lot of rocket space that don't break the equilibrium. I mean, in the pressure system, if you have a hole, you're going to have some kind of interaction with that. I don't say that we're going to destroy the planet, but nobody measure any kind of the rocket leaving the air and breaking all the layers of the atmosphere until reach the space and see something that happened with that. And
Dave, do you want to say one last point? I know you've got.
Can we do them one at a time, and then Dave can go again, and then...
Yeah.
Sorry.
Go on.
So you're asking, so as a rocket leaves the atmosphere, it doesn't leave a hole behind, essentially.
I don't mean exactly a hole, but some kind of interaction of this differential pressure that something maybe escapes.
Yeah, sure.
I'm talking about thousands of rockets, not
yeah, but these rockets in kind of when you take into account how big this rocket is compared to the size of the atmosphere, it's very tiny, you know. It's
very negligible.
Yeah, it is negligible. So I believe that it will kind of locally disturb the equilibrium there, but because of these forces acting on it, you know, it will essentially punch a hole through the atmosphere, but that hole will reform immediately afterwards.
And somebody measured that or see that? Just a question. I mean, for me.
I'm not a rocket scientist, so I don't know.
That's what our theory predicts, basically.
Yes.
Yeah, that's a prediction we can make.
And I imagine that something like that is factored into during launches as well.
Okay. Just one last thing on this. Right, we were just saying about a rising column of air. So let's say a smokestack, you know, heated air going up, going up in the atmosphere. Now that's not all that's happening. Yeah, when that heated air is moving up, it's actually pushing a column of air up. Yeah. It's not just that piece that's moving, right? It's literally a whole column of air being pushed up. Yeah. So that's just one small example, right? Every time the sun rises, the whole face of the Earth is heated up. Yeah, and all that air is now going to be moving up in a huge column. That should, every time the sun rises, right, all the air should leave the Earth, basically. You know, you see what I'm saying? Yeah. Because what you're trying to describe is a state of equilibrium where, you know, gravity balances out this force, you know, of air to evacuate into a vacuum. Okay?
Yeah.
There's an equilibrium. If you change that in any detail, the equilibrium is going to break and air is going to escape.
It's the nature of the dynamic equilibrium that it maintains itself. When an external change is acted on it, it changes the conditions and it relaxes back into the equilibrium
How does that happen? As we said.
So you talk about
when hot air rises.
When you
pushes
talk about
a whole column of air up and out.
Yeah. So as it goes up, it's again the thermal pressure decreases and the gravitational influence decreases.
But now I'm talking about a whole sun.
Yeah. Okay. Yes. So with your sun example, like the heat transfer between particles it's a very complex system. It's not that the sun shines down on Earth's atmosphere and it only heats a layer of air at the top as it hits it. Energy is transferred between these molecules as it comes down.
I agree.
Yeah.
But what I'm saying, we know that when air is heated, it rises.
Yeah, and I'm sorry I don't have more to say, but it's exactly the same thing as I was saying before. As that air is heated, it will go upwards.
And then all of a sudden that mass of air and that velocity just suddenly stops because it's not
like that. It's not a process like that, but it's something gradually happening.
We know how fast air rises. You know, we can watch a hot air balloon work, and we know how fast that rises.
I feel like that's not an equivalence.
Oh, it doesn't rise the same speed as a hot air balloon.
Well, it depends entirely on how their air is heated. I think you can't really draw parallels between the two.
Yeah, well, you know, when it's dark at night and it's cold, the sun comes out, it's warm, yeah, there's a
Yeah, I'm not
great
arguing with that,
thermal
no.
difference there. Yeah.
Yeah.
And also, so the air is affected by that.
Yeah.
And it should disturb that boundary condition.
Yeah, but I'm saying as it's a dynamic, it disturbs that equilibrium state. But because it's a dynamic equilibrium, it corrects itself. It's not like this column of air punches through and just scatters in space.
The
if you know what
example
I mean.
I'm giving you
And
isn't a little hole being punched through.
If we could see
It's
it,
the
if
whole
we could
size
see
of
it in
the
action,
planet.
if we observed it in action, if we could see those molecules in action, it would look very, very boring. It would not look anywhere near as dramatic as you're making
I'm
it
just
sound.
saying that we cannot replicate this idea that you're saying that somehow a pressurized system next to a vacuum can exist. We cannot see that. And I gave you an example, a little experiment to try.
Yeah,
which proves that a pressurized system next to a vacuum.
Yeah, they creates a local, they equalize locally, don't they? Yeah,
Yes.
that's what we agreed on.
So that scales up to the Earth. And
No, because it's completely different. Because you're talking
okay.
a
Completely
gradient of
so
pressure.
then
aren't
you're
we?
saying that at the top of that container there's a gradient of air pressure.
There's a gradient of air pressure all the way up from the surface right up to the
I'm
upper
just
limits of
saying
the
that
atmosphere.
in this container example.
No,
when the air rushes in-
because it's like like you're saying vacuum in the container, normal ground level air pressure outside. If you puncture that container, air's going to rush in. It's going to equalize.
Right. Yeah.
So that's if there was a boundary cutting through that boundary. But this isn't just a solid loads of pressure, no pressure vacuum. It's a gradient going upwards.
So I guess actually something more analogous would be to get hundreds and hundreds of these boxes with various with pressure gradients going up and up and up, and then if you were to pierce through all of them, what you'd find is something much more similar to our own atmosphere. It's not that there's this kind of boundary change at the atmosphere, it's a gradual change as you go up from the surface of the Earth to the outside.
I just want to make one point on this. I think what we're describing, when the sun rises, heats the air rises, and as you say, it's an equilibrium system, other air rushes in. I think we're describing the Coriolis effect, and I think we're describing it without needing a moving Earth. Well, I'm just saying, I think that's how we get the Coriolis effect. No need for a rotating globe to create it. It's exactly air pressure, difference in temperature, difference in pressure, and the system kind of, being an equilibrium system.
Well, again, it's a good idea. It's a nice idea, but it's something you have to prove empirically before you can.
Again,
yeah.
Same observation, two different explanations. Yeah?
Okay, here's some news. Breaking news. This is from phys.org, from a website. It says, Earth's atmosphere is leaking. Every day, around 90 tons of material escapes from our planet's upper atmosphere. Yeah, so it's supporting what I'm trying to say. Yeah, so if 90 tons of material leaks away into space every year, or every day, every day. Yeah. So, yes, save your breath, everyone. So, all of a sudden, when that atmosphere leaves, then you've got a new layer of atmosphere, the new lower level of atmosphere. And now 90 tons of that leaves that day. And then so on, until there's no atmosphere left.
We have to wrap this up.
Yes.
Move on to question
Yeah.
two.
Yeah. Right.
When do people have to go home?
The one thing I would add to that is that this is a model that we have one set atmosphere, and once that air is gone, it's gone forever. We are constantly producing gases. I've produced quite a few today, and and I think you should keep that in mind.
Yeah, good. Yeah, I can vouch for that. He's released some. I fainted for 4 minutes. So, again, I'm loving this. It's really awesome. Number 3. So you're wrong. How would you explain light slowing down when hitting a denser medium and speeding up after leaving that medium for a less dense medium when the law of conservation of energy prohibits such observations?
Sure. So there is a quantum mechanical explanation to this, but I don't think we have time to go into it, and I don't have a whiteboard. So the way that I picture it is that actually light traveling is essentially it hits an atom. That atom absorbs the photon. Electrons within the atom are excited to a higher state, and then they drop back down, and the photon is re-emitted. So here in the air, we have a much less dense system of these atoms than we do in a table. So once you shine the light into a block of glass or something, it's then being absorbed and re-emitted by far more atoms. So it appears to be traveling slower. In fact, it's still traveling at the speed of light.
Just a curious question. Somebody ever see an atom? I mean, there is empirical evidence of an atom, because molecules, supposedly there are empirical evidence, but an atom, even the science says that is unobservable. And just a question. Thing.
Can you guys hear this?
Sorry. Yeah. Oh.
No?
No, I ask for is real evidence of the existence of the particle called atom, and instead talking about molecules, because in my research I come across that nobody can show the particle of the atom. Of course, there are supposedly tiny particles, but it's something that happened the same with quarks or with gravitons or with all these kind of measurements that the quantum physics trying to do for explain the things, but never show. They show just statistic on computer, but actually is some method to actually see the particle, because we are talking about particles.
So in terms of directly seeing an atom, it's impossible. We can kind of indirectly infer it through things like electron microscopy and things, where you look at the interactions of electrons with these atoms and build up pictures of them. So yeah, in terms of seeing an atom, we can't do it. In terms of knowing that there are things there, as far as we know, there are.
So it's like exoplanets then.
You can see some of them.
I see that, but there is not an atom.
Direct image some of the
That is not an atom.
Oh, really?
Yeah.
With recent technology.
Okay. And the last question, which is related with that.
As in, we have.
The last question related with this subject, and that is also if for myself. I hope it's yeah. When we observe the mechanism of the magnets, we're talking about fields, and we experiments show us that this field is perturbed, and we know there is even a magnetic pressure and that kind of things. But however, observates a particle that it's carry on that kind of field, because when we're talking about fields in quantum physics, I believe, maybe I get wrong, there are fields perturbations for these supposedly particles like quarks, graviton, etc. We have something that we can observe as a field of magnet, but there is some kind of particle. Science assign some particles to that interaction of the magnets.
Unfortunately, it seems to have fallen on me. I'm not an expert in either quantum mechanics or magnetism. So, as far as I know, there is a theoretical particle known as the magneton, which is thought to mediate the forces of magnetic fields. Magneton. As far as I know, it hasn't been detected, but you could look to some people at the Large Hadron Collider or something, because I imagine they're looking for it. Cool.
Okay. Questions at the end. if you don't mind. Is that okay? It's just we've just got to give these guys plenty of opportunity. Yeah, is that okay, Nora? Thank you. Can you calculate any? Can you calculate any planet's orbit based on gravity/mass alone when using all masses in the entire solar system and get a result matching the prediction algorithms of the proposed elliptical orbit of any planet? I couldn't say that backwards. So anyway, I can't, but maybe these guys can. So,
This is their question.
no. Well, these are questions to them. I didn't write this.
I can try and sum up the question to how I understand it. So the idea is that using something like Newton or Einstein's gravity, can we accurately predict the orbits of the planets in our solar system? Have I got that one?
Yeah.
Cool. So there's my my Reader's Digest version of it.
Short answer, yes, pretty much. We have a very good idea where all our planets are going in our solar system. We know where they're going to be, and we can continue to predict where they're going to be for the next 500, 600, 700 years. That's because it's based on a really quite a simple system of just pulling in certain directions at certain velocities. I mentioned earlier when I said about Mercury was the one planet we weren't sure how it moved, and that's why Einstein had to come in and I was able to explain it, and now we know exactly how Mercury moves and how it's going to continue to work. I think it was the case, we got it there, of the two planets. Yeah. We didn't actually discover Neptune and Pluto straight away, and yet they were predicted because we found that due to the way the planets are orbiting in our solar system, Uranus, we would expect them to be there. And when we looked for them, we found them. We would not continue to follow these if it weren't for their predictive capabilities. And the same laws help us work out when we're going to have a solar eclipse and a lunar eclipse. Thus, why the news channels are able to tell you and predict it, tell you way in advance, and why you've heard of stories of Westerners going to islands and telling the locals that you're going to have a lunar eclipse in the next 5 days, and then treating them like wizards because of it. It's because they're simple models and it's very easy to do.
1, 2, 3. Lou. I just wanted to make a little point because this is the second time that you kind of wax lyrically about Newton and his theory. Okay. Now you said that Newton's theories, and you before said they were amazing and amazing breakthrough and wonderful and everything. Newton's theories didn't explain everything, right? Now, Newton wrote a huge tome, basically to describe his theory of gravity. He also came up with a whole new way of, calculus, basically, to explain it. Now, when Einstein came along, he gave a completely different interpretation of what gravity is. Completely different. It had nothing to do with what Newton said. So that means everything Newton produced was bullshit. No, bear with me, yeah? If he wrote all this calculus and came up with a theory that didn't quite match, what we observe, yeah? Which means it had no relationship to reality, and Einstein came along and gave a completely different interpretation, which apparently does match up. That means that whole book is bullshit. He made it all up. That's it. So.
I actually totally agree with you. Newton was wrong. Demonstrably wrong, in fact. But
stood for 400 years.
yeah, but you can still apply his calculations to kind of most, certainly everything on Earth, quite a lot of bodies in the solar system. His calculations work, well enough. Sure. He was wrong. This is why I say that nothing is ever fact. That things are just theories until someone comes along and proves them better. I'm sure, maybe in another century, 2 centuries, or whatever, someone might come along and say. and saying that Einstein's theories of relativity are wrong and prove those. But at the moment, that's the best we have, and that's really how science works.
Yeah.
That you just improve on things until you try and get to what you believe to be truth.
I forget the man's name, but a quite important statistician said that all models are wrong, but some are useful. Thank you, yeah, George Box. All models are wrong, but some are useful. And that's the tenets of how science works. We can never prove something to be right. We can only prove what's wrong.
Didn't you just say earlier that saying just a theory was wrong? Because what we're saying is then everything is just a theory. And it will stay a theory until something else comes along to replace it. So everything is just a theory, and that's the correct way of applying.
No, because once again, these are backed in evidence and they have utility. And that's all we can ever want of a model is utility.
Italian had that for 400 years.
And it worked, and we were able to construct bridges. We were able to do a lot of stuff on this planet using those ideas. And that's all you can have. Science, the big misconception is that science will never be able to give you the philosophical idea of truth. It's not what it's capable of doing. What science is capable of doing is giving you a model of which you are able to use and predict. That's all it will ever try to do, and it's doing it very well with the current model.
Can I just add a piece? Thank you. That's a very good explanation. I want to come back to what I first said to you all when we started about the testing, because this is very relevant here. Physics has obviously matured over the last 40 years. I think we'd all agree. Your testing processes are supposedly much better now. Would you agree with that? Obviously, your experimenting tests of new, more fundamental theories is becoming increasingly difficult, actually, not easier, isn't it? Because you're learning more. Many existing theories are so difficult to test that they are widely believed to be untestable in foreseeable future. Would that be fair to say as well?
Where are you getting that from?
I'm just reading verbatim notes that I've made previously.
There are some things we can't.
Yeah, I understand that, and I just wanted to add this final piece, because I just want to get clarity around this. The methods from the past are not working anymore. I think that's fair to say in many ways, because you would agree that you're having to find new ways to test these things. So basically, we're in a very difficult era of science. Thank you.
I agree with you. I think we're in a very difficult era of science, but I think we've always been in a very difficult era of science. It's just that we, as we learn more, we get better.
We all agree we don't know everything yet.
Yeah, like LIGO's unbelievably impressive. There are people out there who 20 years ago, when LIGO was like first in the pipeline, they were like, it'll never be done. You'll never see gravitational waves, and here we are, having seen them.
Just before, I just want to talk very, very quickly. Newton, Einstein. Just 1 sec, Dave. Just give me a sec. just because I got the first 5 minutes. I haven't had anything since. All I wanted to say to you guys was I agree with you, and especially about this misconception about a theory. The whole point is that you can make predictions. Newton's theory, it was okay. It made certain predictions. Einstein's made a bit better. Something will come along and make them even better. Can I ask you why Ptolemy, from the 2nd century BC, was able to make the same astronomical predictions which stood for 1400 years before gravity, before a moving Earth, before a vast solar system, before heliocentrism? Ptolemy had what has now become the almagest, and that stood for 1400 years, making all predictions of eclipses and all the predictions of the planets. Yes, we haven't discovered the outer planets yet, but he was able to do that 2,000 years ago, before any of these, what I'd call newfangled explanations.
A quick. So Ptolemy was a believer in very much a geocentric universe, right? And also I believe that he thought every single orbit was a perfect circle.
Yeah. But
yes.
is that his prediction?
Yeah. Yes. but they became,
the model that worked.
yeah, they became they're very complicated. So, you know, we can explain the orbit of Mars with one ellipse. I think he had to use almost 300 circles. And his predictions were, you know, just the, yeah.
We don't see a perfect orbit.
Uh,
On an elliptical orbit, we still see retrograde motions.
Yes, because of perturbations by other planets in the solar system. Yes, I think that's why. Yeah, I think that's why. Sorry.
I only say sorry. We can assume we assuming that we have elliptical or circular orbits, but we still from here see retrograde motions.
Mm-hmm.
We don't never see a perfect circular or elliptical orbit from outside to corroborate that.
And kind of that's the crux of my argument, that why would Ptolemy try to fit the orbits with perfect circles when they're demonstrably untrue?
His explanations, fair enough, were wrong, but his actual predictions, the theory was correct.
Yeah.
That's all
Exactly,
I'm saying.
yeah.
That's all I'm saying.
Sure.
I still don't think you've got the explanation right, that's all.
Shut down. Right. Right.
Here we go.
Hello. Right. You mentioned detecting gravity waves.
Wait. Just before you continue, so Cardiff has a gravitational waves department. They get very angry if you call them gravity waves. Gravity waves happen on water. These are gravitational waves. I don't know the difference, but they get very bent out of shape.
Right. The thing is, before I was into the flat Earth and everything, I was really well into science, really into quantum physics, Einstein's theory of relativity, the whole works. So when LIGO, was it LIGO? LIGO, sorry, yeah. When they first started doing their experiments, I wrote to Ask a Physicist, and I asked them a question, and they weren't able to answer. Well, they refused to answer, okay? I've asked the same question over the years to various people. None of them answered me, okay? So this might get a little technical, just a little bit, right? So the way LIGO works is that it's kind of like an L shape, okay, with these 15-mile long legs. And what they do is they fire a laser, split the laser into two directions, okay, bounce them back off a mirror, recombine them, and you get an image on a screen, okay? Now, if at any time the distance between the two legs changes, so if a gravitational wave goes along one side, it will change the distance, change the size of that leg, okay? Then there should be an interference pattern on the screen. You agree?
Yep.
Right, so this is supposed to prove Einstein. But what Einstein said is that it's not the gravitational wave isn't in space, it's in space-time. So if space contracts, then time slows down so that the speed of light stays the same. So if you're doing an experiment with the speed of light, you will never detect gravity waves, because if the gravitational wave, so that, yeah, if one leg shrinks slightly because of this gravitational wave, then time would slow down for that beam of light. So it will arrive exactly the same time as the other beam of light. No interference pattern. So if they detected something, that means Einstein was wrong. So if they don't detect something, that also means Einstein was wrong. So what do you got to say about that?
So,
leave it there.
Yeah. This would absolutely be the case if you were doing this experiment with anything other than laser light or light in general. So, whatever speed you're traveling at, if you were traveling at half the speed of light and you fired a laser, you would see that laser go away from you at the speed of light. Yeah. So it doesn't actually matter about the fact that the light is slowing down because it's still traveling at the speed of light?
Yeah, no.
Yeah? Yeah?
Don't try and blind us with bullshit. The point is, you're using the speed of light as the measurement medium, okay? And we're saying, right, that the only way of detecting anything is that that space-time will contract, okay? Now, Einstein says that it's not just space, it's space-time. So they're like a reciprocal. You know, you change the space, time changes, so that the speed of light remains the same. That's the core of Einstein's relativity. So that means it can never detect a gravitational wave.
But, so as the gravitational wave passes through one of the arms, that space contracts or expands. Yeah?
And time slows down.
Yes, but the light is still traveling at the same speed.
Only because time is reciprocal to space. So it has to, according to Einstein, that's what has to happen. That's Einstein. It's Einstein. You can't argue with that. It's not me. It's Einstein.
No, it's not quite one over the other.
It is. That's it.
No.
Oh, for crying out loud.
I'm afraid so. It described it accurately.
But
Go and read it.
But it's still that the beam of light is travelling further.
Sorry, say again?
The beam of light is travelling a different distance.
No, because again, it's space-time. You know, the whole thing of gravity is time and space curving, changing shape, you know, contracting. But the speed of light has to stay the same in Einstein's theory. So, you know, it works the same way in LIGO that it does apparently with the Earth. Yeah. Come on, high five someone.
Drinks are on day. There are people much more knowledgeable about this subject. I'll get them.
Yeah, one's here.
In the words of Tom, so. We are 1 hour 35, would you believe? That is zoomed along. So what I'm going to do is I'm going to give these guys a chance. Is there any questions that haven't been asked that you would like to ask? And secondly, yes, could somebody get these guys some water, please?
No, keep them
right. Can somebody get them 3 cups?
I've got my own.
What are they going to do? Throw water at you? So what I think we should do is give these guys opportunity to ask a question back, as opposed to them always replying to a question. And then after that, I think we should open up to the floor, and then maybe we can always just have like a 1 minute conclusion from each person. I think that is actually a good plan. Does everyone agree? And the other thing I want to ask, while they're getting water, is how has this been received by you guys? Reference doing this again in the future? Is it something you'd want?